Hi, this is Chien-Yi from Microsoft. Today I'm going to introduce you our new method called PatchNet for addressing the challenging face anti-spoofing problem. A robust face anti-spoofing model is very important to assist the face recognition system to block malicious users. Many previous methods leverage pixel-wise pseudo-ground truths as the auxiliary supervision signal to learn more robust anti-spoofing features. However, it suffers from non-accurate ground truths and large computational resources. Another line of approaches aim to learn more generalized binary classifier by adversarial learning, meta-learning, and domain split to address the domain shift issue. However, the adversarial and meta-learning are unstable, and we argue that learning a generalized binary classifier is not practical for real-world anti-spoofing. We observe that the anti-spoofing cues and the textures from the presentation attacks are highly affected by the capture sensors. Using the dataset as an example, it captures live and spoof from very different sensors, so it is hard to distinguish between live capture from low-end sensor and spoof capture from high-end sensor. So instead of building a general binary classifier, we rephrase the face anti-spoofing problem as a fine-grained recognition problem. Similar to face recognition model, we would like to build up an embedding space which can discriminate between different live and spoof types. We claim that the liveness relative patterns are contributed mostly by the capture devices and presenting materials. If a model can discriminate between different fine-grained patch types, then it is already equipped with the capability to detect the attacks or describe the characteristics more precisely. The training pipeline from previous works also suffered from several issues, like a resize input, limited data size, and the need for pseudo-ground truths from non-derivative models. So to address these issues, we propose to learn the spoof-related features by local patches from the row capture. We assume that the spoof patterns are almost uniformly presented everywhere in the capture image, so that we crop patches from row face images and apply some non-distorted operation like random rotation to increase the training data variation and learn robust features. In our training framework, each capture or patch type is defined by its capture devices and presenting materials. And then for each training sample, we crop 2 patches at a time with random non-distorted operation to be the model input. The network is trained with multi-class classification objective with the proposed loss functions. We modify the commonly used aim softmax loss from face recognition and apply different angular margin from diff live and spoof classes to address the asymmetric nature in face anti-spoofing. We also add the self-supervised similarity loss to ensure the consistency between crops from the same capture. For the intra-dataset evaluation, we can achieve state-of-the-art performance on all the protocols in ULU and SIW dataset. We visualize the learn feature by 2D projection, and we can observe that the model can learn more compact boundary and more generalized features by applying the modified aim softmax loss. We also visualize the patch prediction scores on the whole image, and the patch score are consistent across the face regions. Regarding the domain generalization protocols, we can also achieve competitive results with the latest methods by using the fine-grained classification and patch augmentation strategies. The feature visualization of the domain generalization experiments show that capture with similar characteristics will be closer in the embedding space. Our method also enables further application like Few-Shot Reference-based Anti-Spoofing, which will adapt the model by the live anchor samples from a specific sensor. We measure the distance between normalized feature to obtain the liveness scores. For each specific capture sensor in the dataset, we do 5-shot and 10-shot live anchor-based anti-spoofing, and we can improve the spoof detection performance further on each capture device. Furthermore, on the optimized embedding space, we can do patch retrieval to analyze the characteristics of each capture type. For this example, we can remove the live classes from C2 and I, which has 2 low similarity scores with the query sample. Then we can improve some of the protocols by up to 1 to 2% AUC scores. This is our conclusion, and thank you for listening. Welcome to our poster session.